Alrighty. In today's lesson, we're going to be looking at Chapter 8, Lesson 8.1, which is Fundamental Trigonometric Identities. All right, in fundamental trig identities, just like you did in your trig courses, we're going to be using trig identities to help prove one side equals another and to simplify expressions or to even use them to solve for the answer without using a calculator device. So I'm going to basically review just about every single one of these except for the last section. So I'm pulling all the main stuff out of 8.1 so that you have all of the identities so far that we've covered, plus one more section, and then we're going to use those to help us simplify some homework questions. All right, the very first one we see is the reciprocal identities. And again, we've written all of these down before, but now you can have them in one location as you're taking your notes. And you have that cosecant of x is equal to 1 over sine x. You have secant of x is equal to 1 over cosine x. You have cotangent of x is equal to 1 over tan x. And we talked about the flip side of all this is sine x is equal to 1 over cosecant of x. Cosine x is equal to 1 over secant of x, and tan x is equal to 1 over cotan x. Again, that was in chapter 7 that we saw this. We also saw quotient identities. And there was just 3 of these. It was that tan x is equal to sine x over cosine x, and cotangent of x is equal to cosine x over sine x. We then also saw co-function identities as well. And they are cosine of x is equal to sine of pi halves minus x. Cosecant is equal to, or sorry, cosecant of x is equal to secant of pi halves minus x. We saw that cotangent of x is equal to tan of pi halves minus x. And then on the flip side, we saw the same concept that sine x was equal to cosine of, I don't know how many C's I wrote there. That would be cosine of pi halves minus x. And then we had secant x would equal cosecant of pi halves minus x. And then we had tan x would equal cotan of pi halves minus x. A couple of different ones we didn't write down, but they make sense. It was what we call period identities. And remembering that a period for your sine, cosine, cosecant, and secant are all 2 pi, and remembering that tan and cotangent period is pi, you could technically find the answer to a whole bunch of different functions. So sine of x plus 2 pi is this going to be your original sine x? So whatever x is, if I was to add 2 pi, I would go right back to the same spot on the circle so they would have the same answer. So I would call these almost like a common sense identity, but we can definitely use this to help us simplify our answers. The next one is cosecant x plus 2 pi is equal to just cosecant of x. And then when you get into your tangents and cotangents, it's going to just be pi, because that is what their period was. So this is tan x. And then we also have, of course, cosine x plus 2 pi equals cosine x. And then we have secant of x plus 2 pi equals secant of x. And then you have cotangent of x plus pi equal to cotangent of x. We also have our even odd identities, which basically just stated that sine of negative x is the same thing as negative sine x. We had cosine of negative x equal to just regular cosine of x. We had tan of negative x being the same thing as negative tan x. We had cosecant of negative x equaling negative cosecant of x. And then we had secant of negative x equal to just regular secant. And then we had cotangent of negative x equal to negative cotangent. And basically what we saw here is that cosine and secant were even, so we always got the original answer back. And sine, cosecant, tangent, and cotangent were odd, so they gave us the negative of our answer. This last one here, I don't recall doing this with you, but it's one of our basic identities as well, and it's called the Pythagorean identities. And there's three of them. It originates all from this one right here. Sine squared plus cosine squared x equals 1. This is where the next two come from by replacing sine and cosine with cosecant and secant and all these different ones. We're able to develop these different equations. But that's not something we're going to have to prove. You just have to know them. So this right here, the next one would be tan squared x plus 1 equals secant squared x. And the last one is 1 plus cotangent squared x equal to cosecant squared x. So these are the three that you need to know. You don't have to worry about proving it. Now, you, of course, as long as you remember this one, can get to these other three by manipulation. And that's kind of what we're going to be talking about today. We're going to be talking about how do we manipulate these problems using our trig identities. So let's do some examples. Again, I try my best to pull as many from the homework as I can, or at least some that look like it. We'll start with number 1. Again, in this first set, it says use the trigonometric identities to simplify the expression. There may be more than one correct answer. So that you, in most of the assignments, you know, they always tell you get it down to sines and cosines. But when you're simplifying, you're just trying to make it smaller, not larger. So there could potentially be other answers. That could equal the same thing. And on the homework, it should accept all of them. But if you have questions on some of them, why it's not accepting it, reach out and then we can definitely analyze that. All right, but for starters, we have tan x cosecant x. In the book, it has a list of things you could potentially do. One of my first steps that I like to do is turn trig functions into sines and cosines. Start there, put it all in it because all of these functions lead to these two main functions. So using the quotient identity, I can see that tan x is the same thing as sine x over cosine x. All right, so, and that's using the quotient identity. And then using the reciprocal identity, I can see that cosecant is the same thing as 1 over sine x. At this point, I'm multiplying fractions, and I can see I have a sine x in the numerator and a sine x in the denominator. So I can cancel those and then multiply it across what is left. And I'm left with 1 over cosine x. And then again, we want this in simplest form, so the less amount of writing. So again, going back to the reciprocal identities, I can see that 1 over cosine is equal to secant x. So that is actually the answer that you can simplify it to the best of your ability to this point right here. All right, let's do quite a bit more. Let's look at number 2. They can be this easy, and they can be about half a page long and even longer than that when you really get into your more advanced math courses. But let's look at this. So we have 1 over tan squared theta plus 1. My second step is not to always turn things into tan sines and cosines. This is one thing to look at. I feel if I turn these into sines and cosines, I can definitely go a harder route with this. But another thing I want to pay attention to is anytime I have a square, I want to look at my Pythagorean identities. Can I use it to make my equation look a little bit simpler? And in this situation, using the Pythagorean identities, I can see that tan squared theta plus 1 is equal to just secant squared x, or in this case, theta, because that's what we started with. And then with that, using my reciprocal identities, I can see that 1 over secant is the same thing as cosine squared theta. And then that would be your simplified answer. Okay. Let's look at another one. Again, I'm going to try to do as many as I can to help you to have plenty of examples. Number 3 is tan t over secant t. And again, I don't see any squares, so I'm going to kind of default back to my first one. And let's just turn things into sines and cosines. So tangent, using the quotient identity, I can see is the same thing as sine t over cosine t. And then secant, using the reciprocal identity, I can see is just 1 over cosine t. Now, what I have going on here is a fraction divided by a fraction. And we can simplify that by keeping the top, changing the multiplication, and flipping the second fraction. So I'm going to keep the first fraction as sine t over cosine t, change the division problem here to multiplication, and then we're going to flip the bottom fraction. So now it becomes cosine t over 1. And again, multiplying fractions, we can multiply straight across, and I can see that I have a cosine in the numerator and a cosine in the denominator. So I can cancel them, and then being just left with 1, I can see that I'll be left with sine t. And so that is what this will turn into as its simplest form. All righty, so let's kind of go into some more. So let's look at number 4. This one is cotangent squared x minus cotangent squared x times cosine squared x. So I see squares, so I'm thinking Pythagorean identity. When I look at the Pythagorean identity, I don't see anything quite like that. So then my third idea here would be, am I able to pull a greatest common factor out? Am I able to factor it to simplify it in that way to potentially maybe see something different? And I can see that right now I have a cotangent squared x in both of them, in both terms here. So I'm going to factor out the cotangent squared x. And then in parentheses, if I factor out the entire term, I'm still left with a 1 as a placeholder, so that if I was to go back and distribute, I can get back to this point. Now, when I pull this cotangent square out, I'm still left with a cosine squared. So I have a 1 minus cosine squared x. Now, again, bouncing back to number 2 of looking for those Pythagorean identities, I'm going to kind of look and go, I have something with a cosine in it. So alternatively, if I look at sine squared x plus cosine squared x equal to 1, is there a way that I can manipulate this identity to make it look like this guy? And hopefully you're saying, well, I could technically subtract this cosine squared over so that I'm left with sine squared x equals 1 minus cosine squared x. Now I have a new identity. So now I can go, all right, well, 1 minus cosine squared is the same thing as sine squared. So now I have cotangent squared times sine squared. Now I'm in this point here. I've used my trig functions. I've used my Pythagorean identities. I don't think I should use them anymore. I'm now going to go back to that original first step of let's turn things into sines and cosines. You might also be asking right now, it's like, well, how do you know when to use what? If you have like two terms with a square, that's where that Pythagorean identity comes into play, but that's not always the case. Sometimes I will want to do this to be able to multiply something in a later sense to make it even easier looking. So there's no set way. Like I have these steps 1, 2, and 3, and I'm going to actually list quite a bit more. Um, but there's no like you have to do this one. These are just the first things you can kind of look at to simplify your information. But every one of these trig problems are done in a different way. But cotangent using the quotient identity is the same thing as cosine squared x over sine squared x. And if I multiply that by sine squared x, anytime you multiply and divide by the exact same thing, these two things will cancel and I'll be left with a cosine squared x. So that is what this guy pretty much turns into. All right. So let's definitely do more questions. Oh, all right. We'll look at number 5. This one says sine of negative x times tan x. First thing I want to do now is I want to use my even odd identities when I have a negative value. All right, so in this case, I see using my even odd function that sine of negative x is the same thing as just negative sine x times tan x. Once I took care of this negative, now I can turn things into sines and cosines. So now again, tangent using the quotient identity is sine x times sine x over cosine x. Interesting. Okay, so this is where those parts where it's just like, how far do you want me to go? In my opinion, at this point here, I would write this as negative sine squared x over cosine x, but they don't see that as the most simplified section. Typically, what will happen is you might get this question wrong, and then they'll suggest other ways. On the test, I will definitely explain how far I want you to go so that there's no worry. But I would definitely accept this if this was a written test on a test or something like that. But dealing with an online, we have to deal with online situations. But what can be done here is since I do have a sine squared here, I can use the Pythagorean theorem of the cosine squared x plus sine. Well, actually, with that backwards, it doesn't matter because it's plus and it's commutative. But anyway, so sine squared x plus cosine squared x equals 1. Again, if I subtract that cosine squared over, I can see that sine squared x once again is 1 minus cosine squared, just pulling that information from earlier. And they want you to substitute it in here. So that would be a negative 1 minus cosine squared x divided by cosine x. I'll distribute this negative now. And by doing that, I'm actually going to flip it to write it kind of a little bit cleaner. So I want to write this as cosine squared x minus 1. This is the same thing as if you would have said negative 1 plus cosine squared. All right, at this point here, You can now separate these as two separate fractions. So this is now cosine squared x over cosine x, and this is just 1 over cosine x. Now at this point here, because I have cosine squared, that means I have two of them and only one here. I can actually cancel one of them, and I'm left with just 1 cosine x. And then here, using the reciprocal identity, I see that 1 over cosine x is the same thing as secant x. So that is what they call a more simplified answer, even though on a written test, I would have accepted this one as well. All right, let's look at a little bit harder one. Let's look at number 6. Number 6 is 1 over secant squared x plus sine x times cosine pi halves minus x. All right, so in my next step, which I believe is the 5th step, if you have a pi halves, we want to use the co-function identities. All right, so when I'm looking at this, I'm going to leave this right here for now. Actually, you know what I'm going to do here is I'm going to use the reciprocal identity, and I'm going to turn this into cosine squared x. Just because if I don't have to have fractions, I don't want to use fractions. You can make that another one. Get rid of fractions best you can. And then here I have sine, and then I'm going to look at my co-function identities, and I see that cosine pi halves minus x is actually equal to just sine x. All right, so cosine pi halves of the co-functions is equal to just sine x. So then when I look at this, sine x times sine x is just sine squared x. And now looking at this, even though it's not sine squared first, addition is commutative and the order doesn't really matter. But I know now that cosine squared plus sine squared x equals 1 using the Pythagorean identities. All right, so there you go. So all of this big thing right here equals 1. And this actually happens quite a bit. And it's actually kind of cool when something so complicated looking can be something so simple. It's that algebraic manipulation at its finest. All right, let's look at another example. Again, I'm trying to give you all as much as I can. So looking at number 7, I now have sine of alpha. That is what that little thing is called if you've never seen it before. Plus 2 pi times secant of alpha. And again, same concept. When I see at this, I guess this is step 7. If I see a 2 pi, I want to use my period identities. So I see that I have a sine alpha, which is the same thing as an x or a theta or anything like that, plus 2 pi is the same thing as just sine theta. Once I get to this point, I am now going to convert secant into a sine and cosine concept. And when I do that, I now get sine alpha times 1 over cosine alpha. And then I'll multiply these two across. I can't cancel anything, so I'm just left with sine alpha over cosine alpha. And again, I was able to do this using the reciprocal identity. And hopefully now that you see it in this way, you're starting to go, well, that's a quotient identity of just tan alpha. And there's your answer right there. All right. All right, so let's pull another question. We'll look at number 8. Number 8 says sine t times cosecant t minus sine t. Right? In this example, again, best route to go about doing this is to convert things into sines and cosines. So I have sine t using the reciprocal identity. This is 1 over cosine t minus sine t. Now, one of the things was to get rid of the fraction. Here I'm producing a fraction, but what I'm going to try to do is combine this into one term. So I want to see what I can do to actually subtract these, or potentially what might be easier in this sense is let's distribute before I go too far into this. So I'm going to distribute this. So this gives me sine t over cosine t minus sine squared t. All right, now when I do this, I see that sine squared over cosine squared is the same, or my bad, sine over cosine is the same thing as tangent of t. So let's see what we can do with this information. So, oh man, I messed up at the very beginning, which happens. Especially if you get to a place where you're stumped, definitely go back and look at your work. The reciprocal identity of one cosecant is actually sine, not cosine. So when I distribute this out, this will give me sine t over sine t minus sine squared t. This then produces 1 minus sine squared t. And again, manipulating this function here of the Pythagorean identity, I can move the sine squared over just as easy as I moved that cosine squared over in a previous problem to get 1 minus sine squared. So this whole thing right here is actually equal to cosine squared t. I was about to say, because I was like, this doesn't simplify any further. Tangent doesn't do me anything. And then I had, and again, it happens. So I'm glad it did happen, so that you're able to see what you could do. If you get stumped, go back and look at each step. Did you make each step correct? Because usually that is the number one issue. All right, let's look at number 10. 1 over cosine x cosecant of negative x. And again, I'm going to get rid of these negatives. So this now to me looks like a 1 minus or 1 over cosine. Oh my goodness. X and then a cosecant negative x using the even odd functions tells me that the negative can come out. So I'm going to put the negative way over here and call this cosecant of x. This right here is all attached. Now let's turn these into sines and cosines and see where we can go with this. So this is now negative cosine x times 1 over sine x. So when I do that, I see that this is 1 over negative cosine x over sine x, and I see that this is now just a 1 over negative cotangent x. Again, I use the even odd, or I use the reciprocal function here after I use the even odd function, then just multiply it across. Using the quotient identities, I'm able to see that this is equal to cotangent. And now using the reciprocal identity again, I can see this is really just negative tan x. And there might be some other different patterns that you could have gone with to get to that same conclusion as well. All right, let's look at number 12. This one is sine beta. That's what that little weird B looks like. And then tan of pi divided by 2 minus beta, all divided by cosine of beta. All right, so again, this is a pi halves, so I definitely want to look at the co-function identities for this one, and I see that sine beta, that tan of pi halves minus beta, which is the same thing as x or theta, is just equal to cotangent. So this will be now cotangent of beta over cosine of beta. My next move is to turn things into sines and cosines. So this is now sine beta times cotangent is cosine beta over sine beta all over cosine beta. I see when I'm multiplying that If I multiply by sine and divide by sine, they will cancel, leaving me with a cosine beta over cosine beta. And I can see that this right here would just equal 1. All right, so those are all the different types of functions there. And there's 3 more types that's not just proving, but using it to rewrite a given trigonometric function. All right, so let's go into number 13. So I am given that this is the square root of x squared plus 1, and I'm going to tell you that x equals tan theta. So what we're going to do with this information is we're going to take this x value and plug in tan theta in its place. So when I do that, I get tan squared theta plus 1. And then using the Pythagorean identity, I see that tan squared theta plus 1 is the same thing as secant squared theta. And since I have a square root and a square, I know that those cancel, and I'm now left with secant theta as my final answer. So the only difference that we're doing here on this next set of questions is I give you a function, and then I tell you what x is, plug it in, and then now we use our trig function and identities to simplify. Right, so let's do a couple more just so you have a better idea. Let's look at number 14. This is now the square root of x squared minus 16, and we're going to let x equal 4 secant of theta. So if I plug this in, I get 4 secant theta squared minus 16. This square is applied to the secant and to the coefficient of 4. So this now becomes 16 secant squared theta minus 16. Now we're trying to simplify this. Again, greatest common factor when I'm looking at something that's not quite like my Pythagorean identities. So I have a 16 I can pull out, and then I'm left with a secant squared theta minus 1. Now, once again, I don't have a Pythagorean identity that looks just like that, but since I do have the secant, I can look at this Pythagorean identity and go, is there a way to manipulate this one to make it look like this? There is. I can simply subtract the 1. So tan squared x is equal to secant squared x minus 1. So I can now replace this with a tan squared, I guess in this case, theta. All right, now that I have the square root of this, I can separate these into 2 parts. This is the square root of 16, and this is the square root of tan squared theta. And so the square root of 16 is 4, and then the square root and square cancel, so I am now left with 4 tan theta. All right. All right, let's do one more, and I feel like you have everything that you need. So let's look at number 16. This is the square root of 4x squared plus 100. And I have cotan theta equals x over 5. Again, I'm going to substitute this in. But the issue is before I can do that, I need to solve for x. So I got some pre-work I got to do first. So I'm going to multiply both sides by 5. And so really 5 cotan of theta is what my x is that I'm going to substitute it in. So now that I have that information, this gives me 4 times 5 times cotangent theta squared plus 100. And then we'll distribute this out. This becomes 5 squared is 25, and then cotan squared theta plus 100. And then I'm going to distribute the 4. So this gives me 100 cotan squared theta plus 100. And just like before, I'm going to factor out a 100. And then I see that cotangent squared, forgot the square, plus 1 is the same thing as cosecant. So I now have 100 cosecant squared theta. And then again, I can separate these as 2 parts. And the square root of 100 is 10. And then these 2 cancel. So I'm left with 10 cosecant theta. Right? So again, those last three questions are just like what we did at the beginning, just a little bit of algebra where we had them plug it in first and then kind of work it out. All right, hopefully this was enough examples for you. If you need more, please reach out and let me know. Other than that, I see you in the next video.